Assalamualaikum and a very good day to Pak Sandi, our beloved docent. So today, me and my friend would like to present to you about our NLP group project. Before we like someone, we need to know them, right? So may I present to you our group members? The first one is Aizuddin Bin Asman. The second one is Ahmad Alif, which is me. The third one, Muhammad Aris Maulana. What are the topics that we assign to? So the main topic is chart-based passing. When we talk about chart-based passing, we have a lot of algorithm that we can discuss of. But for our group, we will discuss only three. So the first one we have to know about is the definition for each tree. So the first algorithm is early passer. The second one is CYK, Cock, Younger Kasami. And the last one is left corner passing. So, do you know that left corner passing is not an algorithm, but it is a strategy? So, let's look at the first algorithm, which is early passer. Early passer is a general chart passer for nothing CFG. Do you know CFG is? The CFG is context-free grammar, including existing grammar, left recurrence, and ambiguity. Let's move on to the second algorithm, called Younger Kasami, or we can call it as CYK, a bottom-up parsing algorithm used in natural language processing and compiler design. It checks whether a given string can be generated by a grammar, but only if the grammar is in CNF. What is CNF? Chomsky normal form, left corner passing. What is left corner passing? Left corner passer is a hybrid passing strategy, the combination of two different strategy, which is the bottom up and the second one is the top down. It start with the bottom up with the leftmost symbol, which is the left corner, and then apply the top down prediction on the left corner to predict the rest of the structure. So if you still watch until here, which means you already understand the definition for each of algorithm. So let's move on to the next part. Definition done.
For the next slide, we're gonna show you the working mechanism of all the algorithm. As you can see in this slide, we have three algorithm, which is firstly the early parser algorithm, the CYK, which is Younger Kasami algorithm, and the left corner parser algorithm. On the next slide onwards, we're gonna show you how the mechanism works of all the algorithm. Okay, for the early algorithm, it's a chart parser that can handle any context-free grammar, including ones that are ambiguous. It works by combining top-down prediction with a bottom-up completion, which makes it very flexible for many types of grammar. Early uses dot notation to show how far we have passed in a row. For example, A turns to alpha dot beta. This means everything before the dot has already been matched, and everything after the dot is what the parser expects next. Some key characteristics of the early parser are its versatility. It can handle left recursive and nullable grammar, and its performance. In the worst case, it runs in a cubic time, but for unambiguous grammar, it usually uses quadratic, and for some simple grammars, it can even be linear. This algorithm works by maintaining sets of state at each input position, allowing it to track multiple possible passes efficiently. Overall, early is a powerful tool because early is powerful algorithm because it supports many grammar type and manages ambiguity well. Okay, now let's look at how the early algorithm actually works. The parser reads the input from left to right, and for every position, it keeps a set of state called the chart. As it processes each token, it repeatedly applies three main operations, which is predict, scan, and complete. Okay, firstly, The predict, if the dot is before a non-terminal like A to dot B, the parser will create a new state for all the rules that start with that non-terminal. This is basically preparing for what might comes next. Secondly, the scan. If the dot is before a terminal and that terminal matches the next input symbol, the dot moves forward. This means that the parser successfully reads that terminal and adds the updated state into the next chart set. And then finally, the complete part. When a rule reaches the end, meaning the dot is at the far right, the parser looks back to find any states that were waiting for this rule. It then advances their dot as well, since the expected path has now been recognized. These three steps repeat at every position, allowing the early parser to explore all valid parsers efficiently. Okay, for the next one we have here is the CYK algorithm, which is also known as the Koch-Younger-Kasami algorithm. CYK is a bottom-up parsing method that relies heavily on dynamic programming. It's important in theory because it proves that context-free grammars can be parsed in polynomial time. One key requirement for CYK is that the grammar must be in Chomsky normal form, or CNF. This means that every rule must either produce two non-terminal like A equal to BC, or one terminal like A to small a. Now for the process. CYK builds a triangular table which is sometimes called a pyramid. The bottom row represents the input words, and the algorithm works upward by combining smaller parts into a bigger structures. The idea is simple. If one cell contains B and the cell next to it contains C, and there's a rule A equal to BC, then A can be placed in the cell above them. By repeatedly combining these cells, the algorithm checks if the entire string can be generated by the grammar. So overall, CYK is a very systematic, very structured, and guarantees accurate parsing as long as the grammar is in CNF. Okay, now let's look at how the CYK algorithm works in a bottom-up manner. The process starts with initialization. We fill the diagonal of the table with all non-terminals that can produce each input word directly. So if a word matches a rule like A is word, we place A in that diagonal cell. Next is the iteration step. We go through spans of increasing length, starting from length 2 all the way up to the full length of the input string. And then we have the combination. For each span, we try splitting it at every possible point. We check whether the two parts correspond to a rule of the form A equal to BC. If they do, we add A to the cell representing that entire span. Finally, to check for success, if the start symbol S appears in a top right cell, the one that covers the entire input, then the string is accepted by the grammar. This bottom-up table building approach is what makes CYK systematic and reliable. Okay, next is the left corner parser. Left corner parsing is a hybrid approach that sits in between top-down parsing and bottom-up parsing. It tries to capture the strengths of both methods while avoiding their weaknesses. The idea is that it first parses the left corner of a rule, which is the first symbol on the right hand side, using a bottom-up step. Once that part is recognized, the parser switches to a top-down prediction for the rest of the rule. So the process starts bottom-up and then continues top-down. Now, why use a left corner parser? One advantage is that it handles left recursion well. Pure top-down parsers would get stuck predicting something like A equal to A, B forever. But left corner parsing avoids that by starting from the actual input instead of predicting blindly. Another advantage is that it's goal directed. Unlike a pure bottom-up parsers that try every possible reduction, the left corner parser uses the goal category to guide which reduction are meaningful, making the process more efficient. Overall, the left corner approaches offers a good balance between prediction and recognition. Okay, for the left corner parser, the key idea is that it maintains a stack of goals, which is categories that it expects to build. When the parser sees an input token, it goes through three steps, which is firstly, recognize the left corner. It identifies the category of the input word and checks whether it can serve as the leftmost part of a bigger structure. For example, in the diagram, the word prefer is recognized as a verb, and a verb can act as the left corner of a VP. Second, filter. The parser checks whether this left corner category can actually lead to the current goal on the stack. If the goal is a VP and the verb is a valid left corner for VP, then parsing can continue. Thirdly, predict the rest. Once the left corner matches, the parser pushes the remaining symbols of the production rule onto the stack as new goals. For example, from the rule VP goes to verb NP and then goes to that NOM and then the noun and noun. It adds those upcoming symbols so they can satisfy in a top-down manner. So the parser combines a bottom-up recognition of the left corner with a top-down prediction of what comes next.
So my part is implementation of the case study section. First, I want to tell the implementation about the early algorithm. Our case study sentence is astronomers saw stars with Earth. The key here is the grammar recursive rules like NP to NP, PP, and VP to VP, PP, which are the source of ambiguity we need to resolve. Early process starts at card 0. We add the starting rule like top to null s, and the parter immediately predict that expected. It scans astronomers, completing the first NP. This advances the dot to s to NP dot VP. We then scan saw and predict the next pairs. When we scan the word stars, the sentence is practically completed. But due to those recursive rules, it immediately raises the flag for ambiguity. It's predict that PP can take two different places, the NP or the VP. We can scan the rest of the sentence with Rs to finalize that PP. In the final step, the complete PP with Rs successfully attacks to both predicted parent rules. 1. It modifies the NP or stars. 2. It modifies the VP. So the early parser successfully find the valid meaning for this. Okay, after that we next the CY key is a bottom-up parser that absolutely requires the grammar to be in COMC normal form or CNV, and we are testing the string we BA using the triangular tables. We start at the bottom, which is the initialization layer. We fill its cell by feeding the single non-terminal that generates that specific input symbol. For example, B is generated by B and A by IC. We move up to row 2. Here we use dynamic programming to combine cell from row 1, checking if the combination matches any A to B C role in the CNF grammar. If it matches, we add that non-terminal like S or A to the cell. The combination continues for row 3. We check every possible split point of the three symbol substring. This is the core of this dynamic programming efficiency. We continue this systematic process for row 4, always building upon the result of the rows below. Finally, we check the top cell or 519, which is represent the entire string because the star symbol S is found in the cell. The string we BAABA is accepted by the grammar. For the last, we move in left corner parser implementation. We use the same sentence again. Astronomer saw stars with Earth. Left corner is an effective hybrid approach, excellent at handling difficult grammar structure like left recursion. Parsers begin bottom-up astronomers in recognized as the left corner on NP1, then it switches to top-down to predict the rest, expecting a VP. When stars is found, VP1 south or south stars is completed, and the NP to NPPP and VP to VPPP ambiguities are instantly activated. When width is encountered the PP stars, this PP then need to attack to both the NP or stars and the VP or south stars. Ears completed the PP, and the parser follow both paths and successfully computing option 1 or NP attachment, and option 2 is VP attachment. For the final output shows that the left corner parser, just like early, successfully found two valid parsers tree. This demonstrates is strong control over the parsing process, and especially with ambiguity.
Let's move on to the weaknesses and strength for each algorithm. For early parser, the first strength for early parser is handles any CFG, including left recursion and ambiguous grammar. The second one is works well for natural language. If you know that, natural language is usually messy and ambiguous. The next strength is it can produce all parse trees using a shared parse forest. Last but not least, no need CNF conversion. So grammar stays simple. Okay, and I can say that early parser algorithm is efficient for many real world grammars. So what about the weaknesses? The first weakness for early parser is the worst case time is O n cube. It can be slow for very ambiguous sentences. The next one is more complex implementation compared to simpler parser like CYK. The last one is performance drops when grammar has a lot of ambiguity or many prediction. Yes, so let's move. The next algorithm we need to talk about is CYK. The first strength for CYK is it use a simple systemic dynamic programming method. The second one is it works very well with probabilistic PCFGs, especially for Viterbi algorithm. The next one is it always give the correct result, but there is a catch. As long as the grammar is in the CNF, it will give the correct result. Since the CYK use and related to CNF, it make the CYK time consuming because the grammar must convert into CNF first, then it will get to processing. The time complexity for CYK is very and always cubics, so it becomes slow for sentence that long. It is not incremental also. What does it mean by that? The meaning is it cannot be passed text that comes in step by step like streaming input. Yes. Enough talking about CYK. Let's move on to our last algorithm. Oh, wait, the last strategy. The left corner parser has some several advantages. It handles left recursion very well, making it more efficient compared to the pure top-down approach when dealing with grammars that naturally expand on the left. It also supports human-like incremental parsing, meaning it process input in the way that resembles how human understand sentence piece by piece. However, it has some weaknesses. So, for example, the left parser is harder to implement compared to CYK, requiring more careful handling of rules and states. So the next weakness is it is also less general and less documented compared to the early. So there are fewer clear regulations, clear guidelines, and standard implementations. Finally, its behavior vary depending on how it is implemented. So, which can make the debugging and the consistency more challenging. That's all about the weaknesses and strength for the left corner part. That's all about the strength and weaknesses for this algorithm and strategy. Congratulations, you already understand the strength and weaknesses for each of these algorithm. After all the discovery, the exploration, and the research that we do during the group assignment, overall we can say that no algorithm is the best for everything. We use CYK when you need strict dynamic programming, CNF grammar, and probabilistic parsing. We use early when you need maximum flexibility and general CFG support. And when you want efficient incremental passing and good handling of left recursion, we use left corner passing. Yes. So that's all about conclusion. To end this presentation, I would like to thank to our docent for hearing this presentation and watch until the end. That's all from us. Thank you very much and have a nice day.